Now, our ultimate goal is to use samples to make predictions about the parameters of a population. To do that, we form estimators, or statistics as they're called, from the random variables in our sample. So how do we know that we've chosen the right estimators? How do I know that I'm actually picking some method that is going to measure the correct thing? And to help us understand that, we're going to talk about this concept of bias. Now, in everyday language and English language, biased means that you systematically favor some outcomes over others. Right? So if you are biased towards red cars, that means you will generally favor cars that are red over others that aren't. Now, we want to extend that idea into something more quantitative, something more precise. So we are going to define mathematically the bias of an estimator as the difference between the expected value of the estimator and the thing it's trying to estimate, the parameter. So the best way for us to proceed is that we are going to hope that our estimators are unbiased, so that they are actually centered on the correct thing that we are estimating. But on the old bathroom scales, there used to be a dial that you could adjust, and it was a strange dial. It always felt rough and bumpy, but nonetheless, that dial was used to adjust it so that the resting measurement of the scale was 0. And that meant you were unbiased. When the needle on that estimate showed 0, you were ensured that you would have an unbiased estimate. Now, your weight would fluctuate day to day, and those fluctuations are normal. They're never going to be the same, but you're ensured that when you set that dial, you're never going to be reading 5 pounds heavier than you normally would be. So we are going to focus on a couple of things. Is the sample average an unbiased estimator of mu, the population average? If it's to be unbiased, we need to calculate the expected value of the average. Now, we are going to assume that, as before, each one of these xi's are identical and independent and identically distributed. And we are going to assume that they all have individually this same average value, expected value. So we know from our work on linear combinations of random variables that this is given by the following. So if we go through and we do the work, we are going to find that, no surprise, if we use the properties of expectation, we are going to find that there's a common factor of 1 over n out front, and we'll get n mu over n, which just ends up giving us mu. So by definition, we can say that the sample average is an unbiased estimator of the population average mu. So what does that mean for us? When we start getting into the data analysis and data collection, it will make sense for us to compute the sample average. It'll make sense for us to go through and do this calculation. Because if it were biased, then we would be systematically getting the wrong number with this calculation. So we want to make sure we're performing the right calculation. The other parameter that we are interested in, so the population variance, is given by sigma squared. So if we assume again that our xi's are iid, and that we assume the variance of each one of them is sigma squared, we would like to estimate this. So what is the right estimator? So the first thing we have to do is define an estimator. right? Which mathematical calculation should we do with the random variables to get a number, to get some sort of outcome? Now, you might recall that a while ago when we defined variance and we defined it for a discrete random variable, we talked about defining things like this: xi minus mu squared times the probability. This was way back when. We are going to use this as motivation to define something called the sample average. So we'll say that the sample average S squared is given by a very similar idea. We'll take the sum of the values in our sample, but rather than writing mu, which is what we really want to write, we can't use that because we don't know what the value of mu is. So instead, we have to use the next best thing, x bar up here. Now, underneath, because I know what's coming, I'm going to put some sort of value here. So if I were to use the probability measures successes, right? So normally you would say, well, let's divide by the number of outcomes. For the meantime, I am going to put some value of k down here. Is S squared, it's a capital S squared, an unbiased estimator of this population variance? Now, this calculation is a little bit longer, so I'm not going to go through the details, but it turns out that if you're to take the expected value of S squared and do the work, it's nothing but algebra and then using definitions, you will end up getting n minus 1 times sigma squared over your value of k. This means because it's not equal to sigma squared, that means it's biased. It will systematically favor the wrong thing. Doing this calculation won't get us a good estimate of the thing we want. So if I want this to be unbiased, the only way to do it is to set k equal to n minus 1. The sample variance, and sorry, I wrote sample average up here. It should be variance. So the sample variance, the definition of sample variance should be as follows. S squared is going to be the sum of xi minus x bar, all squared, divided by the sample size minus 1. As n gets really big, there's little difference in n versus n minus 1. S squared is an unbiased estimator of variance, but the square root of S squared is not an unbiased estimator of just plain old sigma. You have to be careful with that. They are not the same. That square root adds a completely different set of calculations in there, and you can't do that. So going forward, we are going to use these two estimators when we start studying data sets.